This is section 3.2, and we're going to deal with linear programming. You are asked to solve things graphically, and you're asked to either find a maximum or a minimum value of a function. The function is called the objective function, and you must satisfy a set of restrictions, and they're called the constraints. So in order to do this, you want to graph the constraints and find a feasible region. So let's look at an example of this. So the question might read, find the maximum value of the objective function z equals 3x plus 4y, subject to these constraints. 2x plus y is less than or equal to 4, negative x plus 2y is less than or equal to 4, and x and y are both greater than or equal to 0. You're supposed to graph this. So you want to graph each of these equations, and I changed each of them into y equals format. So if you take this one, you had y equals negative 2x plus 4, okay? And that is this line here. And then this one, you had 2y is equal to x plus 4 divided by 2, and you get y is equal to 1/2 x plus 2. That is this line. So we know that we're in the first quadrant. This x greater than 0 is here and y greater than 0 is here. So we're in the first quadrant. And then we graph those two lines, and I did that. Y-intercept, slope, that's this line. This one is this line. And so where they overlap is this green area in here. That is your feasible region. And so you have some intersections, some corner points. So you can find those by setting these two equations equal and finding where they do intersect. You can do that on the calculator, or you could do it by hand. So you get these corner points. So we have 2, 0, 4/5 and 12/5, and 0, 2, and of course this is 0, 0. So at the corner points that we've defined right here, we're going to plug in. We have 3 times the x value, which is 0, plus 4 times the 2, and so that gives me 8. Remember, we're plugging into this. At 2, 0, we end up with 6. At 4/5 and 12/5, we end up with the number 12. So as you look at 8, 6, and 12, 12 is the maximum value, and that's what you were looking for. So let's kind of recap that. You're given an objective function subject to these constraints. So you turn those, you graph those constraints as lines. They were all greater than and equal, so that's solid lines. We graph it, find out what's enclosed, that's the feasible region. Find what the intersecting points are and evaluate at the corner points. Find either the max or the min, whatever you were asked to find. So that should be enough to get you going on the problems. Let's look at the problems for 3-2. All right, for the first one, it says the graph to the right shows a region of feasible solutions. So we've got this given region. It has the corner points already designated. Find locations of the minimum and maximum values of the given functions. So we have A is one function, and B is a different function. So we're going to do everything 2 different times. So the maximum value is 62, and the value is located at 2, 8. How did we get that? We took z equals 7x plus 6y, and we put in the 4 corner points, 2, 8, 6, 3, 3, 1, and 0, 4. There's a low point here and a max here. So that's what we filled in. 62 is the max, it occurs at 2, 8. 24 is the min, it occurs at 0, 4. And then you do the same thing with the other function. we're plugging in the same points in a different function, and we get 6 is the min. Let's see, 6 is the min, and 26 is the max. So you're given the picture and the corner points, you're just plugging them into the functions. Same thing with this one, and I didn't show the work, but you are plugging in the corner points. The maximum of the function is 16.5 and occurs here at 0.11. The minimum value is 0 and it occurs at 0.0. The max is 18 for that function and it occurs at 6.4, and the min is 0 at 0.0. All right, number 3. Same thing, we are asked to find max and min values. Now, what we should notice, this is unbounded. This is going to go on, if this graph were extended, it would go on forever. So there is no maximum, and so you could choose that right here. The maximum does not exist. All right, the minimum of that one is 23, and it occurs at 2.5. So you're going to plug in these points in each of these functions and find the max and the min. Again, for B, the max doesn't exist, the min is this, and you can try those, plugging them in, making sure you get that. 3, max doesn't exist, there's the minimum. D, same thing, max doesn't exist, the minimum is 10.5. All right, so those are just giving you a picture with the points. We now move to where number 4, solve the following linear programming problem using graphical methods. So we've got an objective function and we've got these constraints. Again, turn each constraint into a y equals so you could graph those. I used my calculator, and I have one of the lines here, and I have one of the lines here. And where do they overlap? That's right here. And they want to know the minimum z value. And we had to find this point where they intersected and this one, because this is just y equals 0. And so that's going to be 8, 0, where that hits there. So we had those to plug in. We had 2, 9, and we had 8, 0. The minimum turns out to be 16. Plugged in both points in the objective function. So on this one, we had to graph it. We had to find where they intersected and plug those points in. And again, you can find that by doing intersect on your calculator. If you're doing it on your calculator, you could do second calc, number 5 for intersect, and enter 3 times. So if you were right around this area and you had both those lines in, you could do second calc 5, enter, 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 and you would get this point as an intersection. And you could do the same with y equals 0 and this line. Or you could do it by hand and set this part equal to this part, and you should get the same thing. Number 5, had the graph there. I just colored it in yellow so you could see it better. Again, you've got you're going to maximize this. That's your objective function, subject to these constraints. You've got a horizontal line at y equals 9 and a vertical line at x equals 3. And then you've got the other line here and a green line here. So that's where I turn them into y equals. And if you set 5x minus 15 equal to 9, because we had one that was y equals 9. You come up with 24/5 comma 9. So that would be right up here. And then we also had, so I think I've got all the points labeled up here. This one is at 3,5, this one is at 3,9. This one you find by intersetting 5x minus 15 equal to 9. You set the two y values equal, and you get 24/5 comma 9. This one is the intersection of the blue and the green line. So down here, I did that and got the 29/8 and the 25/8, or you could just do it on your calculator and have it in there, and when you graph it, do second calc intersect and find the intersection of those. You'll get it in decimals, but you could convert it easily to fractions by doing math and fraction, and you would get that. So we have those values, and when you plug in these points, you're trying to maximize, and what you end up with should be 234/5, which occurs at the 24/5 comma 9. So this one is our maximum. Okay. All right. Is that it? Is that our last one? I think that is our last one. So that should get you going on maximizing and minimizing, finding the feasible region, and evaluating.